Hello and welcome to another IoT Central webinar. I'm David O'Hara and I'm the Managing Director at IoT Central. I'd like to start by thanking Telit Cinterion for sponsoring today's event. Today's webinar is the first in a two-part series. It's titled Clearing the Road for EV Adoption with Reliable Connectivity, Part 1. Now, let me introduce our speaker. Neil Bosworth is the Head of Segment Management at Telit Cinterion. Neil, when you're ready, let's get started.
Thank you, David, and it's great to be here with IoT Central. And in this webinar, we're going to discuss how secure, reliable connectivity plays a critical role in paving the way for electric vehicle adoption. And part one implies there's part two, where we will continue with a technical deep dive. So let's start this webinar with a brief market overview, starting with the trend that's driving this rapidly developing industry of EV charging. Electric vehicle adoption has been growing exponentially due to falling costs, improving technology, and also government support. And globally, 10% of passenger vehicles sold in 2022 were all electric. And this is a significant increase from just 5 years earlier. Norway has a whopping 80% of new vehicle sales being all electric. Iceland, Sweden, and the Netherlands are followers with between 25 and 40%. And this is followed by China at 22%, which is significant as China is the world's largest vehicle manufacturer. The rest of Europe follows, with the United States being at 6%, but growing rapidly. And by the end of the decade, as many as a third of all vehicles in North America will be electric. Now, this growth is driven by market trends as well as carbon neutral policy efforts in a move towards renewable energy. Furthermore, the infrastructure investment being deployed to support adoption makes for a robust market outlook for EVs. But there are, of course, a few hindrances. Fluid government policies trigger surges and drops in demand, and the creation of a robust, reliable, and fit-for-purpose public charging infrastructure, well, that remains a challenge. An infuriating situation for electric vehicle drivers is an out-of-service charging point. At the edge of IoT deployments, there are various potential points of failure that have potentially huge implications for the wider application. And in the context of an EV charger, or EVSE, IoT technology is responsible for communication with the grid for tasks such as sharing load balancing data, for accurate payment and billing data, enabling remote maintenance and management of EVSEs, or conveying information for effective consumer interaction. But undoubtedly, the quality of customer experience significantly influences customer loyalty. Charge point operators bear substantial costs due to unreliable, sluggish, or dysfunctional charging stations. And these costs manifest in terms of revenue losses and damage to a brand's reputation. Range anxiety is a term we've all become acquainted with, but this is somehow predictable or controllable. Charge anxiety is the real issue. If a chocolate vending machine is out of order, well, that's kind of just a minor nuisance. But if an electricity vending machine or mobility or freedom vending machine is out of order, well, that's another matter. And to be fair, there's quite a few things that can go wrong with EVSEs, but there's undoubtedly a growing reputation for unreliability. And this has given rise to a few government programs. For example, back in September last year in the US, the Biden-Harris administration announced it's opened up applications for the Electric Vehicle Charger Reliability and Accessibility Accelerator Program. And that's one heck of a mouthful, Mr. Biden. But it will provide up to $100 million in federal funding to repair and replace non-operational EV charging infrastructure. A new EV charging charter has been unveiled in the UK, and this is aimed at raising standards and improving the experience of charging electric vehicles. So the implementation of effective charging systems is driven by several factors, such as government initiatives, And in order to optimize the charging experience and maximize driving range, thereby reducing this charging anxiety, there's an intrinsic need for all EV users to get charging points deployed massively in public and private areas, at home and at work. So the number of charging points is increasing, and over the past few years, charging stations have evolved from being non-connected to devices that are now smart devices that rely on wireless connectivity. In fact, over 70% of the total install base is expected to be connected by 2026. The total number of dedicated charging points in Europe is forecasted to grow at a compound annual growth rate of 34%, from 4.5 million in 2021 to 19.6 million by the end of 2026. And in North America, Berg Insight estimates that the total number of dedicated charging points will increase from 1.4 million in 2021 to reach 6.1 million in 2026. Again, growing at a CAGR of 34%. And these numbers include both private and public charging points. But let's not hide here. Connectivity is the enabler of many value-added and essential features of EV charging infrastructure, but it's also its Achilles heel. Whether it's bad design, poor planning, or the influx of new manufacturers racing to gain a foothold on the best locations, there seems to be a real lack of design for robustness. So let's take a look at 3 use cases that drive the adoption of wireless technology in EV charging infrastructure. Smart charging success hinges on secure, interoperable standards and protocols. And these are essential to aid the widespread adoption of a smart charging infrastructure and ensure seamless integration across different EV manufacturers and supporting entities within the ecosystem. And it's fair to say the smart charging landscape is marked by fragmentation as numerous standards and protocols compete for widespread acceptance. Nonetheless, certain standards are gaining traction over others. EV charging stations must connect to a back-end system that manages the entire charging network. And one prominent protocol facilitating this connection is the Open Charging Point Protocol. And this is advocated by the Open Charge Alliance. Now, OCPP enables EVSEs to link with compatible charge station monitoring systems, defining the necessary operations and messages for effective network management. The OCPP integrates with the ISO 15118 standard, addressing vehicle-to-grid power transfer, and plug and charge, which allows EVs to automatically identify and authorize themselves to compatible EVSEs. And all these features rely on strong cybersecurity that's being built on digital trust between the EV and the EVSE. Another important protocol is the Open Charge Plug Interface, which oversees e-mobility service providers, or EMSPs. This protocol allows EV drivers to access multiple charging networks through a single RFID tag or an app, simplifying the charging experience across various providers. And additionally, the Open Charge or the Open Smart Charging Protocol provides an open communication channel between charge station management systems and smart charging service providers. And these SCSPs, often grid operators or demand response aggregators, utilize OSCP to balance energy management. Now, it's important to note that the link between the CSMS and chargers represents a potential weak point. This is operational technology. Some of it's IT, but this is operational technology, which is formed by a connection, which is usually wireless, and it must be meticulously designed and managed to ensure robust functionality. Without a reliable link, the entire smart charging system is flawed. Taking a look at these wireless connections, public charge points, such as those found at fuel stations, car parks, or motorway service stations, often utilize DC fast chargers, or DCFCs. To initiate charging, customers typically identify themselves using an ID card, a mobile application, or even just the use of a direct credit card. Now, both Wi-Fi and Bluetooth technologies have a role to play in establishing communication links between users, installers, and in fact other EV chargers. And as I just mentioned before, the ISO 15118 standard is the communication between the vehicle and the charge station, which can either be supported via power line communication or Wi-Fi. And Wi-Fi is the standard to support vehicle communications according to ISO 15118 Part 8 for wireless power transfer. But due to the fact that most stations today use a cable, PLC is the most popular implementation. Whilst it's common for public chargers to have their own dedicated connection to the cloud services, it's also possible for single EVSEs to be used as a master node with other close by stations connected in some local star or mesh network via Wi-Fi, Bluetooth, or some other ISM technology. Now, looking at the back-end side, in public charging infrastructure, single charging nodes can connect via LTE to cloud services provided by charge point operators. And alternative configurations may involve IP-based wired connections, with cellular being used as backup. EV charging infrastructure is capable of delivering up to 350 kilowatts to vehicles, and this significantly impacts the grid. And this kind of elevates EV charging to critical infrastructure status, not solely for transportation, but also for intelligent grid edge strategies by distribution system operators. Now, we always say best practice IoT involves remote monitoring and maintenance. And for EVSEs, remote management addresses challenges unique to dispersed systems lacking on-site technicians. And this encompasses monitoring and controlling systems spread across an extensive geographical area. Remote management has a few roles to play. Firstly, it needs to securely distribute authorized firmware updates, performance enhancements, adjustments to communications configurations, and security patches to EVSEs. And this also includes their embedded cellular communications modules. Secondly, remote management needs to detect anomalies in device behavior to identify potential security breaches or network operational issues. And it needs to manage digital identities, security keys, and credentials. And this is done at scale to maintain secure access and authentication. Now, remote management is an integral aspect of the broader EV charging infrastructure, addressing the unique challenges associated with longevity, security, and again, this geographical dispersion of charging devices. This management strategy must accommodate the nuances associated with cellular communication and must be considered holistically. That is an integral element of the system from the start of the design. Remember, cellular communication is a complex ecosystem, and the cellular module is in fact a complex subsystem. And just to finish off this picture, finally, the services provided by the charge point operator include location and reservation. And there's also the opportunity to provide value-added services, making use of this screen or the display, or also maybe provide a hotspot for a captive market. The semi-public use case considers hotels, residential complexes, and business car parks. And it's similar to the private use case, but more often multiple charge points are networked using wired or Wi-Fi or Bluetooth mesh arrangements. Due to location, it's also possible for them to make use of the local network within the host site. Nonetheless, cellular communication is used either as a primary connection or a backup, and it's subject to the same device management care and attention to deliver a robust performance. Now, considering private charging, we're seeing a greater need to connect the EV charger for smart grid and smart home applications. The expansion of home charging is putting huge pressure on the domestic grid, and this was never designed to address such loads, but it brings other demand-side management opportunities such as flexible tariffs, encouraging or even forcing EVs to be charged at off-peak times. And grid managers can also remotely control the amount of energy available to the EV chargers. And of course, this V2G or vehicle to grid. This is using the vehicle battery as storage to support the grid, or as a BTM, a behind the meter power source. Fundamentally, to support such schemes, the EVSE needs communication in residential settings. And this can be directly to the back end via LTE or making the use of the host Wi-Fi. Now, cellular is the most reliable way. It's not subject to the inconsistencies in the communications equipment outside the control of the EV service providers. Now, there's also a requirement for communication with the electricity meter, either via some HAN interface or via the P1 port of the meter. And the smart metering industry are releasing very interested distributed intelligence initiatives to address grid edge behavior caused by EV charging. Now, again, unfortunately, there's a lot of fragmentation with home area network protocols. EEBus and Matter are two examples of IP-based HAN delivered over Wi-Fi for smart home applications. So in general, EV charging, like most IoT systems, is a fairly low bandwidth application with data transfers of, say, 100 kilobytes. But we do need to consider overhead applications such as device management and firmware upgrades that might be a file in the megabyte scale. We also need to think about coverage, which is twofold, both the availability of the network in a geography and the signal strength in hard to reach locations such as parking lots. Let's take a look at the technologies and how they fall within the 3GPP evolution. And this is the 3GPP defined roadmap for cellular comms and IoT and broadband. Technologies for EV charging mainly fall within the mid-speed IoT category and possibly the efficient low-speed branch. You'll notice this ultra-reliable low latency term in the middle. This isn't necessarily a product offering. There are no chipsets or devices for URLLC. It's more a set of requirements or aspirations that can be adopted by the delivered standards to address the applications they're required for. The sweet spot of industrial IoT is LTE Cat 1, mainly due to its exhaustive coverage. The service level expectation has driven two evolutions, both within LTE and 5G. So LTE Cat 1 BIS is not new, but over the last couple of years, it's rapidly gained traction as a simplified LTE Cat 1. And NR RedCap is the 5G standard designed to address this low to mid-speed application area. It actually brings 5G into the IoT arena. It begins its life with a speed performance similar to that of LTE Cat 4 in release 17. Machine type communications are LTE Cat M and narrowband IoT. And with narrowband IoT, you need to be prepared for long latencies. In fact, too long for practical EVSE designs. TCP/IP is not suitable for narrowband, and running a protocol such as OCPP over MQTT is likely to cause timing issues. And looking to the future, LTE still plays a role in 5G networks. LTE will continue as 5G offers a lot of flexibility and many options for LTE coexistence. So MNOs will continue to support LTE-M and narrowband IoT, even beyond traditional LTE sunset, which let's say is sometime in the 2030s. But it will be most likely still based on the 4G evolved packet core. So looking a little deeper into the technologies that are most suitable for EVSEs, the simplest is LTE Cat M. It's attractive because it's like baby LTE with a path to 5G. And it's also cost effective, but one needs to be aware of a few aspects that might affect reliability. Firstly, although there is coverage in most countries, you'll find that not every network operator supports it. So there could be some coverage holes that simply can't be filled. Secondly, roaming. Operators are now managing roaming agreements aggressively, and MNOs are readdressing the initial strategies they employed to encourage use of the networks. Consequently, networks are introducing a connection fee for roaming, which could well catch you out. And finally, enhanced coverage is a well-advertised feature of Cat-M, and it's really designed for indoor applications. But be aware, though, that not many MNOs support enhanced coverage mode in LTE Cat-M. Moving up the scale, Cat1 bis, which is essentially LTE Cat1, but it does away with the second diversity antenna as used in Cat1. Everything else, such as the protocols and the data rates, they're pretty much unchanged. RX diversity of Cat1 improves RF reception, especially at the edge of the cell. But to support RX diversity, the LTE Cat1 chipsets need a complex RF front end and complex software to support the second antenna, which can in turn require a more complex PCB. Now, the Cat1 bis standard enables simpler and cost-optimized modules for the single antenna, and designers can exploit this to design simpler, maybe smaller, and certainly lower cost IoT applications than they could with the original LTE Cat1. However, with Cat1 bis, you can expect to lose an additional 3 to 4 dB compared with Cat1 due to this single antenna approach. For 5G longevity, NR RedCap will fill this space, and it's now in its early release under release 17, which as I said before, it's of similar performance to LTE Cat4. And RedCap will continue with release 18, which introduces lower power and reduced complexity, taking many of the features of the MTC technologies. The important factor here, though, is longevity. This is 5G technology, and it will be around for a long time. And to ease into this technology, the RedCap devices also support LTE Cat4. Telit Cinterion is a company that's been making cellular modules since their original introduction into the market in the mid-90s, and we've delivered hundreds of millions of them to address the most challenging, mission-critical IoT applications. The cellular modules across the portfolio are industrial, secure by design subsystems, a communications computer, and they're designed to ease the integration of cellular technology into industrial IoT systems. But when I say ease, for the most reliable design, it's essential to understand how these devices interact with the network and build an AT command structure which is designed for robust performance. I'll not go into details about the part numbers here, but you can see the core devices we would aim towards EV charging. Devices that fall in the same footprint are designed to be migratable with reduced effort to build a PCB that supports multiple options. So you'll see a migration path from MTC through to 5G. And switching between technologies does take some effort to ensure correct operation. Don't think you can just switch a module and everything will just work. We have global SKUs and devices optimized to fixed geographies, and they all support some embedded processing to run applications internally via Linux, ThreadX, or C. They also have embedded agents for device management, and this is another feature that can address lifecycle management and therefore improve reliability. And you'll see the lineup of cellular modules includes an LTE Cat4 based smart module. And when you consider the building blocks of the electronics of the EVSEs, they're made up of a few common systems. You've got communication for both short range and wide area. You've got feature-rich displays and a touchscreen and some capable processing environment to run the core protocols, the security management, or all the things that you need to run. And a smart module massively reduces hardware design effort, and it also reduces the verification effort and also the logistics. And it does this by integrating what would be a complex PCB into a single component. And this would reduce the risk of component failures and oversights in hardware design. And taking this approach, it changes the whole designer concept. The low voltage electronics has a design process similar to that, let's say, of a consumer gadget. And the development can be done as a software application on Android and soon Linux. And of course, we've got all the necessary support tools, so you can start your journey with a readily available development platform from us. Now, Sometimes manufacturers like to integrate off-the-shelf communication for a hardware design that's done and proven and tested and complete, and all the approvals process is completed. And this is a simple option for cellular backhaul, and it's to integrate one of our IoT gateways within the enclosure of the EVSE to give a very reliable and quick implementation. The gateways are driven by the same AT commands as the module, but through industrial plug-in interfaces, ideal for connecting to PC-based architectures or programmable logic devices. But again, remember, the construct of the AT commands is key to the most reliable design, and this is true of both modules and gateways. As a supervisory device or even a retrofit, you can write an application that resides in the gateway in ThreadX or C so as not to interfere with the main processor of the EVSE. You end up with a standalone communication system with interfaces to the part of the main system via general purpose input-outputs or via the standards-based interface. So let's spend a few minutes to look at the short range lineup. Remember, Wi-Fi deals with several use cases for the front side, such as dealing with multiple EVSEs in a master-slave format, communicating with vehicles using ISO 15118, or connecting to smart home apparatus using smart protocols such as Matter and EEBus. And on the back side, or the cloud side, EVSEs may wish to use the in-prem broadband network via a router. So Wi-Fi 4 is the dominant technology in the IoT space. It can operate in the 2.5 gig or the 5 gigs range using single or multiple antennas. The subsequent technologies add higher data rate and higher network efficiency to ensure overall throughput is improved, especially in congested environments. For EV charging use cases, the data rate isn't particularly high and not that important. So Wi-Fi 4 is good enough, but interesting, Wi-Fi 6 is gaining traction for future-proofing, and it also offers some tricks to trade data rate with coverage. There are two kinds of solution or product types. On the left side in green are the IoT MCU modules embedding a full Wi-Fi stack from Wi-Fi 4 to Wi-Fi 6 in either single or dual band. They also support BLE, Bluetooth Low Energy, and have options with or without integrated antennas while supporting smart home standards such as Matter. On the right side in blue, these are what we call IoT companion modules, from Wi-Fi 5 single in, single out to Wi-Fi 6 multiple user MIMO. A companion module means that an external Linux or Android processor is necessary to run the stack, and these modules support both station or access point modes, and of course BLE. And it's the choice of the designer and the architecture of the system that dictates the choice of module type. If the application architecture is based on a Linux or Android-based implementation, you can attach a companion module via SDIO or M.2, making use of the IP and networking stack within the host. You can also use our Linux-based Cat1 or Cat4 cellular modules in conjunction with a companion Wi-Fi module for an easy LTE and Wi-Fi management coexistence solution. Alternatively, Architecture 2 uses the host processor to apply AT commands using the UART, SPI, USB, or SDIO with the Wi-Fi stack embedded in the module. And Architecture 3 makes use of the internal processing capability of the module for a completely standalone Wi-Fi solution. So before we continue, let's just stop to the review. There are a plethora of choices to connect EVSEs. So far, we've discussed hardware options from a simple yet intelligent IoT gateway, embedded modules, smart modules, but there's also the option to go for PCI Express or M.2 interface versions of the embedded modules for an adaptable design. But just be aware of the changes in network configurations or the performance or the reapprovals required when opting to plug in a different card. So far we've talked about some of the ingredients, the hardware modules suitable for reliable and robust connectivity. But we want to work with our customers not just in a traditional supplier-customer relationship, but in a broader long-term partnership model where we help customers take their solutions from concept phase through integration, activation, and operation. We know that the electric vehicle charging industry use cases will bring different needs and complexity across the 4 phases of the IoT journey. And Telit Cinterion will propose a fully tailored offering solving the specific pain points unique to each project. The first phase is about evaluation of the best fitting technology. And this would consider the general application concept, the communications needs, the specific needs for your EVSE design, the subscription to connectivity, and the considerations of regional and global SKUs, and the overall business model. The second phase looks at the integration of Telit Cinterion products and the services into the EVSE application. And this is made up of design and bill of materials optimization, performance optimization, application verification. We also help through approvals and compliance and help integrate any external platforms. The third phase is the actual deployment with commissioning and activation of the EVSE in the field. And the time to market is accelerated through fast and flexible deployment, looking at the best subscription selection to a mobile network operator, device configuration and registration and secure cloud involvement, and of course, device activation as well. And the last phase brings everything together with the continuous operation and maintenance of the EVSE solution in the field through the entire life cycle. And here we leverage remote management tools for remote configurations and updates for the module or modem, the application, and maybe also security as well. And we can also look at the device status and analytics, the performance optimization, and again, optimizing the subscription throughout the life cycle of the charging station. So let's take a look beyond the module and gateway hardware into network connectivity and device management. One of the greatest EV charging challenges is supplying a reliable network connection to ensure always-on connectivity. If the cellular connection becomes unstable or disrupted, transaction speed will get impaired, and this could hamper revenue opportunities as EV drivers will just simply search for alternative charging points. The worst case scenario, the bad connection could jeopardize the functionality of the EV charging station itself, damaging customer experience and eroding brand reliability and reputation. Therefore, it's crucial to understand how these charging stations establish communication with network and the underlying interaction between the cellular module and the carriers. Frequently, charge point operators employ a roaming SIM card, granting access to multiple operators within a specific area. And this strategy offers a reliable connection to the network infrastructure, mitigating risks associated with a single network operator's outages or congestion issues. The capability to control the device's connection to the infrastructure, this translates to heightened resilience and uptime. Telit Cinterion is a full tier 1 MVNO, a mobile virtual network operator with a unique position in the IoT industry. By engaging with our customers at the very beginning, we become their partner for the lifetime of their devices or projects. We offer SIM cards and industrial connectivity rather than consumer-grade connectivity services, covering 600 carriers in more than 200 countries. Now, these connectivity services bridge across various networks, operators, and network technologies. Networks are increasingly particular about roaming agreements for technologies like CAT-M or traditional LTE standards such as LTE Cat 1. And our IoT-centric connectivity framework enables us to guarantee the presence of these roaming agreements, therefore fulfilling the connectivity needs of charging stations. We equip managers with portal-based tools to influence the connectivity of edge devices. This could involve steering a device away from one network operator to another, or even altering the entire subscription in extreme cases. For instance, if a roaming agreement's about to lapse on one particular carrier, we can remotely provide a completely new subscription through our tools, ensuring uninterrupted connectivity. This capability is of huge importance for devices that need to operate in the field for several years, probably decades, without needing on-site engineering visits. And on-site engineering visits, it's a truck roll and it's an expense that can be substantial with also high consequential costs. Telit Cinterion have worked hand in hand with the GSMA to deliver new IoT-specific solutions for eSIM subscription management. We can combine the features of multi-IMSI roaming strategies with the ability to completely renew the chosen connectivity service across the lifetime of EVSEs. Of course, it's essential to design the communications hardware and firmware together to capitalize on such strategies, which is why we engage with customers at the start of the design. Bolt-on afterthoughts are likely to lead to an unreliable charging infrastructure. And let's just think about device management. So there are lots of focus given to the way the application is working, making sure that there are insights about how the charge point is behaving, whether it's delivering the necessary power, the payment, the load balancing, the uses, etc., and how much it's being used. But potentially not enough focus and attention is given to the communications path, which isn't necessarily connected to the application. OneEdge brings insights into the health of the cellular module, which is a single subsystem responsible for the smooth running of the entire system. And when I say subsystem, it really is that, with thousands of lines of firmware running a complex processor which runs the 3GPP protocol stacks, it runs the power management, the radios, etc. And just like a cell phone, it needs firmware updates and security updates over its lifetime. In fact, this is mandated in the US and it soon will be in Europe. And remember, cellular networks are like live animals. Their configuration can change over time. So you can use OneEdge to keep your modules updated and make any remote tweaks required with a ready-built secure platform. Another benefit with OneEdge as a device management platform is it's bonded to the same cloud platform as the connectivity management platform, meaning you can derive insights from both the SIM card side of the connection, such as the radius logs from the MNO or the MVNO, and combine those insights with information about the nature by which the module is connecting to the infrastructure. Now, this brings a forensic level capability around making sure the module, hence the EVSE, it registers and it's able to create a socket connection or HTTP or whatever protocol the EVSE is using, and provide the resilience needed to be able to sustain data transfer to the charge station management system. And if something happens at the application layer, having the insights from the device management side will at least help you understand why it might have happened, rather than just being another dead EVSE waiting for a man in a van to come and fix it. Now, this is a complex topic, and we'll do a follow-on webinar as a deep dive in the coming weeks. This combination of physical products along with cloud connectivity services can be somewhat perplexing. Dealing with multiple entities to provide just one part of the EV charging solution can be a logistical challenge, especially for pure play suppliers providing both charging equipment and charging services. So we propose a unique solution combining everything you need for a reliable connection to charge station management systems, and we call it Connected Module as a Service. For a simple monthly payment, we can deliver cellular modules and connectivity and device management platforms without the upfront investment of purchasing modules. So for maybe less than $1 a month, you can get everything as well as support required to get your charging station connected. You can see we have a broad suite of solutions for EV charging applications. If it all seems complex, we can also do designs and manufacturing of communications solutions for integration into EVSEs, combining our vast knowledge of IoT hardware, cellular networks, RF design, and volume manufacturing to deliver turnkey solutions, including the hardware and really the background intelligence to make the most reliable connected charging solutions. So I've said a lot today, and if you have any questions regarding today's session, please don't hesitate to ask using this link. And on the website, you'll also find a dedicated section to EV charging in the industries menu at the top of the page. So this concludes the discussion regarding electric vehicle charging for now. I've discussed the rise of the industry, the impacts of poor reliability, and some of the challenges solving them. We looked at the communications hardware and the services to aid a robust design. And in part 2, we'll cover topics such as understanding the device hardware, using a strategy for handling the AT commands, using the URCs, and the resilience of how the modules work with the network, and leading you on to how to make the connectivity robust. We'll talk about the use and benefits of device management, and also about the cellular infrastructure and any sunset considerations you might have. So until then, thank you very much for joining me.
Well, thank you, Neil. That was really insightful. This brings our webinar to a close. I'd like to thank Neil for his presentation and Telit Cinterion for sponsoring today's event. You can view more webinars at iotcentral.io. Thanks for watching.